All right, I think I have make it live on the YouTube. That's my. Oh, I do not need to do that. Yeah. I only needed to do this. Can I take off my mask? Do you mind?
Let's just do it.
I wear a mask kind of out of breath.
Talk 1 hour. Really struck me on how to phrase the first sentence. Actually, the first one.
Okay.
So.
Nice.
Interesting.
Yeah, I'm using Zoom to live on the YouTube. So. You can.
This is like my
cat
food. What? You have chocolate cat food? No. But it's like you have a crispy outside and also like some ingredient. Okay. Kind of fancy cat food.
Did you say something about a cat?
Yeah.
So what are you?
I mean, Stormy really like a kind of cat food similar to this one, but not chocolate, of course.
Right.
Yeah.
You were asleep when I told Brandon this. I got a message from my friend who said, you know, the refrigerator soundproof, or sorry, it says the refrigerator is not soundproof. In fact, you can hear when something meows inside of it. The cat has been stuck in the refrigerator for 3 minutes.
Is Nathan coming?
I
think Nathan.
Meeting.
Yeah,
Okay.
Nathan and Brina, they have a meeting, so they will come later.
Okay, I'm sorry that haven't got a chance to practice the photos, just finish the editing. So if you have any suggestions, comments, questions, I'm very welcome that. So.
Do you have slide numbers?
That's right, I have, yeah. So slide basically, except for some pages, I will almost have everyone, yeah.
I'll be right back again.
Okay.
I'm in the wrong glasses. I can't see.
Oh, that's not prescription.
They are, but it's just a lower prescription for a computer.
Glad you bring your own water. I do not have any drink spare.
Oh, that's fine.
I mean,
There is a fountain.
I do not prepare for any beverage for you.
You can drink this tea.
Nah. It's
a lot of black peppers. Wow.
only have 5 days. 5 days? Yeah, 5 days.
On Friday.
I mean, only have 5 days until I define.
Oh, 5 days.
Yeah, and after that, I still need to work. Nah,
you're already a doctor. I grant you a doctor.
Yeah, your order is not worth. Close enough.
Now I should be able to see.
Yeah. We'll be on this PhD defense, but we will not grant you the master.
All right. Okay, I think let me check if anyone is on my YouTube. I think no one. Yeah, no one.
On YouTube, not on Zoom?
Yeah, I only send the YouTube link. So
okay. Do you ever test the YouTube link? Or do you are you confident it'll work?
I already tested that.
Okay, cool. Okay.
I mean, if you want to, you can check that out right now.
Only for you.
Yeah.
Okay.
So. Okay. I already share my screen. Yeah. So, and let's start. I think maybe you do not need to take notes because I already have a live on YouTube and I can replay that.
Oh, okay.
Yeah, if you think it's a little trouble, so you do not need to take notes anyway. Okay. So yeah.
Do you want me to figure out how long it is?
Oh, you do not need to do that. I think I have time here. So okay. That's good.
Perfect.
Yes. Okay. So I will start. And again, sorry that I don't have time to practice. Okay, so good afternoon, I'm everyone, and thank you for coming to my PhD thesis talk. And in my defense, I will mainly talk about the atmospheric chemical system on Venus and the ice shear on Enceladus. Mainly, I will focus on the mechanisms that control the variations of these systems. So my advisor is Xi, and I have worked with my advisor for 4 years. And first, I will show you this outline of my thesis structure. I will mainly talk about 2 parts. Part 1 is about the Venus atmospheric chemical system, and the second is about the ice shear on Enceladus. For the first part, I will separate it into 2 small parts. The first is about the temporal variations of this chemical system. Sure.
So, if you have some problem, do you want to stop in the middle and we can point it out, or just after an hour you want, because we may
I think you can ask in the middle, and also I will pause for a second, pause for a minute when I end one project. So
okay, so you have 3 products. We can talk about each one.
Yeah. Okay. Thank you. And first, first small part is about the temporal variations of chemical system. Second is about the local time variations of this chemical species on Venus. So let's first see the Venus project. So Venus is very similar to Earth in mass and radius, but the current environments on these 2 planets are so different. This makes us wonder why the 2 planets have evolved so differently. So this is critical for us to understanding the evolution of terrestrial planets. So studying Venus atmosphere is a good aspect to understand this planetary evolution. So about the Venus atmosphere, we can think currently we know that the Venus atmosphere is very thick, and from the surface, which has the temperature of over 700 Kelvin, and to the 50 kilometers, this is called the low atmosphere, which is not easily to see. And from 50 kilometers to 70 kilometers, we have a global coverage of clouds, which is made by the sulfuric acid and the water. Above the clouds, we have the middle atmosphere, or sometimes we call it a mesosphere, until the 100 kilometers. So this part is the main focus of my thesis defense. And in this middle atmosphere, the photochemistry is so strong and so complicated. And actually, we can observe the spatial variations and the temporal variations of chemical species in this region. Currently, we have the observations from Venus Express and also other spacecraft and ground-based instruments. We have found that the species like sulfur dioxide has exhibited strong variations. For example, on the left, I show you the temporal variations of sulfur dioxide around the cloud top, which is around 60 kilometers. So from this left plot, we can see that it has a decadal decay, which may be attributed to the volcanism on the surface. But currently, because of the because of the global coverage of clouds, we cannot easily to validate this surface process. On the right, I show you the spatial distribution of sulfur dioxide observed by a ground-based instrument. And this shows that it has the plume features and its spatial distribution is so patchy. So we want to understand why this kind of stuff happens. So my question is, what process analyze the spatial and the temporal variations of these chemical species in the Venus atmosphere, but mainly in the Venus mesosphere? So first, I want to understand the temporal variations of the sulfur dioxide and water we have observed. The Texas IRTF has been for the first time observed the co-evolution of the two species around the cloud top. So the first species, on the left, I show you the temporal variations of the two species. We can see the two species, how the two species change with time and how the two species correlate with each other temporally. We can see there is a, if we draw a trend line for the two species, we can see the two species may have the anti-correlated pattern. So, okay.
No, sorry.
I'm too nervous. Okay, so we want to understand what's the process behind this kind of temporal variations, also the anti-correlation. Especially for the anti-correlation, what mechanism should be the reason for this kind of phenomenon? So we have two hypotheses. On the left, I show you a sulfur cycle. From the surface to the clouds, the sulfur dioxide is transported upwards, and in the clouds, it will be transported by convection and eddies. And then above the clouds, sulfur dioxide will have the photolysis and reacts with species and finally consume the water to form sulfuric acid, which is the main component of the clouds on Venus. So currently we have two hypotheses for the anti-correlation. One is about the sulfur chemistry above the clouds, which is because in this chemistry, it says that the sulfur dioxide and water consume each other. This may give us the anti-correlated pattern. Another stuff is that we think about the eddy diffusion, which is says the vertical mixing efficiency, which may influence the species variations. Could this eddy diffusion also give us this anti-correlation? So these are two hypotheses I want to test in my first work. To test this, I use a 1D chemical model, which has been developed for decades. So this model is basically made from the John's paper in 2012. It has involved over 50 species, 41 photo-dissociation reactions, and over 300 neutral reactions. So this, I use this model to simulate the middle atmosphere, which is ranging from 58 kilometers, which is the middle cloud top, and to the 112 kilometers, which is below the homopause. So in this region, only the eddy diffusion is significant. You can ignore the molecular diffusion. So, in our simulations, we vary the lower boundary mixing ratios of two species, sulfur dioxide and water, to represent the lower atmosphere perturbations, which may be caused by dynamics or the volcanism. So from our simulations, I will show you the dependency of sulfur dioxide on the lower boundary conditions. So to the left, this plot has an x-axis of water mixing ratio as the middle cloud top, that's our lower boundary, and the sulfur dioxide mixing ratio as the vertical axis. So the color here represents the sulfur dioxide mixing ratio above or near the cloud top. So, and the white dot and the white lines separate this parameter space into 3 regimes. The white dots means the case that matches the observations. So we can only focus on the white dots here. It locates in a regime which has the sulfur chemistry controls the relationship between the sulfur dioxide and water. So in this regime, the sulfur dioxide and water will will consume each other and form the sulfuric acid. And if we choose a random case in this regime, the random case will also give us the anti-correlated pattern of the 2 species. So this says that the sulfur chemistry is the reason for the anti-correlation, while the lower boundary perturbations, the lower boundary mixing ratio changes can explain the temporal variations of these 2 species. And then we go to the second hypothesis, which is about the vertical mixing. So I changed the vertical mixing in our model and try to find how these 2 species are related. So the color here means the transport efficiency. From the darker color to the brighter color, the transport efficiency is increasing. So you can see when we increase this transport efficiency, the sulfur dioxide and water are positively correlated. So this says that the AD diffusion alone cannot explain the anti-correlation. Okay, so this is basically what I did for my first work. Is basically about the temporal variations of 2 species observed by the ground-based instrument, and I combined the 1D chemical model with these observations to explain its mechanism. My main takeaway is that the sulfur chemistry is responsible for the anti-correlation, while the lower atmosphere perturbations may explain the temporal variations. The vertical mixing alone in our model does not work for this phenomenon. And this may have the implications of the importance of using the sulfur dioxide and other chemical species above the clouds to indirectly infer the information in the lower atmosphere and even the surface process. So that's the rough structure of my first work. Any question right now?
Actually, have a few science questions.
Okay.
Not really. I think your presentation is good, but I really have a few science questions. It's like the first one is like anti-correlation. Could you switch to that slide? I think you will get some questions like, you really believe those anti-correlations, right? Because
yeah, those.
I mean, these lines are drawn by myself, but someone has to do the quantitative calculations. The anti-correlation is about 0.7. So, I mean, the correlated coefficient.
Correlation coefficient. Yeah.
No, go ahead.
Correlation coefficient is one thing, but there is it is possible this just due to about the uncertainty. Have you done any like t-test to show the statistical significance?
No, this is just the result from my co-author Thesis work, and she did all the things. And in her paper, she says that there is an anti-correlation.
It might help to just like show or cite her paper and say like this is what the coefficient is, so that people don't question you.
Already cited that.
But you show the number.
Oh, number. Okay, got it.
Not just the correlation coefficient, but the like statistical significance.
Okay.
Do you know if it would help to see the plot of the 2 values against each other instead of the time series? Just see like the concentrations against each other. Because then like you can eyeball an anti-correlation really easily.
But I want to show the temporal
I
ratio.
mean, well, I assume that that's in the paper,
Okay,
right?
okay, got it.
Because I feel like if you remove the sulfur dioxide observation from 2014 to 2015, and afterward it's kind of like flat, right?
Yeah.
Yeah, that's true.
And those 3 dots is really like
That's right.
very good uncertainty. I don't understand why. You cannot really see the error bar.
Yeah.
God.
So that makes me suspicious.
Not just correlation coefficient, but like the statistical test parameter.
Yeah.
Like I'm sure she did some test for significance.
I'm not sure. I'm not sure I can find it in her paper. Maybe she did it by herself.
If she did it, she would have said it. So
Okay.
you might go,
Okay.
because that is something that like, you know, a reviewer could ask me like, why is this significant?
Yeah, I think the committee is going to ask you this question. Like, you have how many years observation? 1, 2. I think it's around
10 years. Yeah.
10 years could be very large uncertainty, like statistically. If you think about the standard error, it is proportional to the 1 over square root of the sample size.
Okay.
So that is like 30%. That is large. Right? So yeah.
Okay, I will check that. Yeah. Yeah. This is the base. This is the basis of my first paper.
Yeah, I think this is not the first time that we ask you this question. So
yeah, maybe in my qualified exam we also asked.
Yeah, because you presented before and we asked you the similar question. So I think this is worthy to investigate.
Got it. Okay.
And the next one is in another chemical network. You show the reaction with sulfur dioxide, sulfur trioxide, and also sulfuric acid. Next, yeah, this one you have to say. So, is it possible that you have the reaction between sulfur dioxide and water? They can be removed with each other, right?
I think in real sense, the 2 species does not react directly.
They react.
They react?
Yeah.
Maybe in the Venus atmosphere.
H2SO3.
Oh, you mean that way? I think that's not a stable species, right? And in the Venus atmosphere, this chemical pathway is not significant. In our model, we do not include this pathway. So I.
Do you know the reaction rate?
No.
But I think this is worth it because
I think this one is the main pathway how the sulfur goes to the sulfuric acid. Yeah.
All right. Because if you pump sulfur dioxide into the water, it would dissolve in it.
Yeah, I agree with that.
But in the atmosphere it's different because it's not as like in the water, but in the atmosphere it's in gas. So I don't know.
Okay, I'll ask Xi about this.
Yeah, if you have the number in your head, I think it's fine. You say
because in our model we do not have this chemical pathway, so I do not have any numbers about that. Yeah.
We didn't find it on the list website.
But you need to think about the temperature and the density of the atmosphere, and then you need to calculate. Yeah.
I think the pressure is about 1 bar, right?
1 bar is around the middle cloud. This is about 70 kilometers, so that's about 0.1 bar or 0.1 bar.
This is fine.
Yeah.
It's probably
fine.
The paper doesn't have an obvious significance test, which is shocking.
Yeah.
And it never plots them against each other, right?
Okay.
A lot of plots and not the obvious one. Can you go to slide number 4?
Number 4.
What are the yellow boxes in that arrow?
Oh, yellow box is it's incoming solar flux, and the red box is the thermal radiation by the clouds. So
what are the slashes?
Slashes.
Like what does 30/75 mean?
Which one?
100 slash.
Yeah. Like why are there 2 numbers?
Oh, 30/75. Okay, so
You're really pushing her.
think you're good
If it's
and
in your plot, people are gonna wonder what it means.
Yes.
It was a
That's
little
right.
distracting, yeah.
Like take it out if it doesn't matter. It's fine. Also, what's the downward yellow arrow? Is he flowing into the planet?
Yeah, yes. I think
No
there are
way.
some
Still in equilibrium, right?
There's no way Venus is heating up on it.
Yeah,
It's
yeah,
cooling
yeah.
off.
yeah, but still I think there's still a small amount of sunlight will reach the surface.
Reaching
But
the
it-
surface.
reaching
that
the
looks like
surface.
it's going into the surface.
Yeah.
The arrow goes below the surface.
Below the surface?
Look at it's hitting into the surface. Like it goes below the surface.
I think
It
it's
tells you
just
it's
the
hitting the
joint
surface.
issues.
What?
I mean, I think it's just the joint issues below
That's
the
a really bad drawing issue.
Yeah.
um,
Like the head goes like.
Okay, I will check
Yeah,
this
you
camera.
should
Yeah,
check this paper.
yeah, I will
if you're
check
not going
this
to talk about it, just take all of those out.
Okay,
You
okay.
can draw a cloud and then.
Yeah, I can draw by myself, but it's easier for the others
I think it would also help.
because it's beautiful.
You say 100 kilometers when you're on the slide. This is not a beautiful picture. I'm sorry. You said 100 kilometers.
Uh-huh.
100 kilometers isn't on that plot, so I think it might actually
Yeah.
help if you showed more of the atmosphere,
Okay.
so that you can point out your region.
Okay.
Yeah, that would really help.
So if you showed like 0 to 200, then you can say, and I do 50 to 100.
And also plot with pressure and temperature could be used
Oh,
instead of
Yeah.
the radiation.
in fact, I have that picture, but I'm thinking everyone knows that it's boring to show that.
That's okay.
No, that's more useful.
Yeah, it's not much
Wide
more
talk, so not everyone in the department knows Venus, so we're-
Okay.
like, that would be a good figure to show them.
Especially when we talk about chemistry, pressure and temperature
Mm.
matters, right?
Yeah, this plot is confusing because
Hmm.
unless you want to talk about the yellow boxes.
You don't think this plot is nice?
Get distracted.
If you want, I can remake it in 5 minutes if you want. Like this is not a hard plot. It's a fine plot.
Okay,
Yeah,
okay.
I'm sure that for the paper it was really nice, but for the talk, like I kept looking at the
Ah,
boxes, being
okay.
like, what does that mean? And then you didn't.
I
talk
got
about
it. Yeah,
so
yeah. Maybe it's not a
It's just
problem for my
distracting.
paper. Yeah.
If you want me to make this plot, I will do it. Like
I
it
mean,
will take
I
you
can
5
do it.
minutes
I
in
can
this
do it.
plot.
In fact, I can do
Like
it
I can
just
make it prettier than this.
just I'm lazy these days.
This is a PowerPoint.
Yeah, I'll use Illustrator and it'll be even prettier
I mean,
with a texture. It's
this
a fine plot.
this picture is
This
made
is
by
beautiful.
This is
by
good.
That is really
Yeah, this is
this is
good.
made
This
by
is good.
myself, so I can make it, but it's just lazy. I'm just lazy.
Although the one thing about this is you didn't comment on the volcanic flux,
Mhm.
which just like kind of stands out. Like you might say, do you assume something about the volcanic flux? Like it's a boundary condition, I guess.
Oh yes,
You might want to say what you assume about it.
but our model is the middle atmosphere model, so it's basically the
Let's do it on
58 kilometers. So I cannot surely say that it's from the volcanic flux, but
But you still have boundary.
that's right.
Like when you
So-
draw it on there, people say, okay, so what is it in your model? And so
Ah.
just say like, say what you do with it.
Mhm.
Whatever it is, even if you say we don't understand it, like I think it's worth just like referring to,
Mm,
like maybe the volcanic flux is the source of the anti-correlation. I can think of ways to do that.
okay.
And I think you need to charge your laptop.
Really? No.
It's 50%.
50% is enough. Yeah.
Okay.
58 minutes. I also have the power saving model, so that's
Slide 10.
I think.
What is the difference between log 10 of SO2 and SO2 in ppm?
It's just I didn't know. Oh, okay. Oh, yeah. Our ppm is axis. Okay. So ppm is 10 to minus 6. So log 10 to log 10 SO2 is just I do not use the unit of ppm. It's just 10 to minus 6 is just 10 to minus 6. So
But then why are the lines, why is it curved at all? Shouldn't it just be the like
mhm.
so if you have like 2 ppm, right? Shouldn't that always be like right here, like a little orange, and shouldn't it just be orange? And then this would be like yellow.
That's this is the SO2 at the different levels. So
Oh, you need to
So-
say that.
Yeah, that would be really.
these are the middle cloud top, which
Okay.
is 58 kilometers, and this one is at 64 kilometers,
Okay,
which is
same.
one cloud top.
So what is the XY axis?
I would put that right here. Like just say
Oh,
log 10
okay.
SO2, above the make it clear because
Okay.
I don't actually remember what you said on the slide. I was trying to figure out what that
Okay.
color bar
I'm
was.
still confused. Like, so XY axis, they are still mixing ratio?
Oh, that's still mixing ratio.
And what is the color bar? Color bar is still
Color
mixing
bar is
ratio.
still mixing ratio, but that's sulfur dioxide at the cloud top.
Oh, all right. So it's a boundary condition.
Yeah. Middle
Okay.
cloud top is
Okay.
middle cloud. There are two cloud tops.
Oh,
Middle cloud top is a boundary. Cloud top is around 70 kilometers. So that's
Okay,
different.
that needs to be clear.
Yeah.
maybe
So this plot is the axes are your boundary conditions and the color is your output.
yeah.
Okay, yeah, you need to. Huh.
Yeah, that's a difficult.
Your axis labels.
I know that.
you can just say the boundary condition.
Other the boundary.
At the boundary.
Okay, got it.
You don't have to remake this figure. Just do the word.
Yeah, the word needs to change though. What if it was like?
Sorry, making figures make sense is important. They're like something I like think of. Yeah. What if you said H2O boundary condition
Okay.
and then ppm
In ppm.
and then the same thing here, and then you say you need to say middle cloud top somewhere.
So you have two layers of colors.
Yeah, the cloud has 3 layers. So middle, lower, middle, and also
But
the
in
high.
your fourth slide, you have only 1 layer of color. So that is confusing.
Yeah, I needed to say the layers of cloud.
I
Okay.
think if you search the cloud on Venus, you can find many figures that you can be satisfied with these.
Yeah, I think it's actually okay. Instead of middle cloud top, maybe just say like at 58 kilometers and then 75 kilometers or whatever.
Yeah, that's clear. Yeah. Okay.
I don't know exactly what to say, but
Mm.
and maybe just out loud say that the axes are your boundary conditions and the color is your output.
Okay. You been using the text to say that out?
I think you can say that with words.
Okay.
The text needs to say the altitudes. I think you can say with words the purpose.
Okay. Yeah, it's I think it's a very tricky plot. Yeah, sometimes always make people confusing every time I press.
So you really need to take care of.
Yeah.
Okay. Yeah, I will try to slow it
Another way to
down.
do it, and this takes a little bit more time, but you can you can put up the plot,
But cover up the interior, so make it blank, and cover up the color bar, and say this is the situation we set up. Like in words, you say this is the situation we set up, and then we calculate the resulting value inside, and then you show the color. So show the context,
Oh, I got it.
covering the colors, and then explain the goal, and then show the color.
How do you take out the color?
You put a white box
over
over
it, yeah.
Oh, okay.
I mean, there are other ways to do it.
Yeah.
It's a white box. And cover up the color bar. So you say you don't show people what the result is until they hear you say the goal.
Got it. Okay. I think that's a good way. I will do that. Yeah, definitely do that.
Yeah, so they're not distracted by trying to figure out while you're-
Yeah. Also, I don't really get what the white lines are.
I couldn't figure that out either.
White line is just some artificial line. I separated regimes of this parameter space.
But you only have dots in the bottom left.
Those are the cases that match the observation.
You just take them. But then, like, why do you even extend the plot farther? Like, why not only zoom in on the thing you have here?
It's just to show it has different regimes. If I want to only explain the observation, that's right. You are right. I can only show this kind of small regime. Yeah, that's right.
Okay.
Yeah, but we have 3 regimes. Yeah, I do not talk to the 3 regimes. Maybe I.
You said there were 3 regimes. I just didn't really understand why they matter.
Yeah.
I'm also like, why is the bottom left a different regime? Why isn't it just a diagonal line?
Oh, that I will have some backup slide, but right now I don't have. It's determined by both this for the sulfur dioxide around cloud top. I also have water around cloud top. For both stuff, for these different regimes, the sulfur dioxide and water changes with the lower boundary condition in different ways.
Okay.
So that's why it has 3 regimes.
Okay, I think you should say that. I think you should say these are regime boundaries that include more information than what's shown here.
So the white
okay.
line is the boundary of two regimes.
Yes.
But I feel like the real boundary of two regimes is like something like
Yeah, I agree.
It's artificially, you can say that, yeah, it's not correct. I just draw by my hand. So
Yes.
All right. So, but you can figure out from the gradient, I guess.
Grading?
Gradient. There is a clear gradient idea.
Yeah.
Oh, you mean that gradient? Yeah.
I think you have the largest gradient.
Yeah.
Oh,
You're right. Yeah, the largest gradient is located.
yeah, you can tell. It's kind of like tilted. Yeah. Anything you show in your slide, you have to explain it. That's a
I mean,
principle.
it's is that I needed to understand them. I can explain, but I do not need to explain them.
No, everything you show, you have to explain.
Everything you should, you need to. I
Everything
mean,
you show, you have to.
that will take a lot of time.
Well, no, the thing is, if you don't explain it, why is it on the slide?
Yeah.
Just take it off the slide if you're not explaining it.
Okay.
Like a mistake people make is they put paper figures on slides. You don't have to. Like paper figures are always denser than slide figures. You don't have to put the whole paper.
That's right.
So yeah, it's not that you have to explain everything on the slide. It's that don't put it there if you don't want to explain it. It doesn't have to be there.
Okay.
Because otherwise you're just gonna lose your audience.
Yeah.
Okay.
Like I don't remember what you said on the slide, so I was trying to figure out your figure.
Yeah, they said difficult.
Also, I'm sorry. I need to leave it like
I will remake.
4:10. I'm gonna have to leave a little bit early.
Okay, that's okay. Yeah, I will remake this blog. It's kind of tricky blog. Anything else?
I'm really enjoying how neat your slides are. They look really nice.
Thank you.
Yeah.
Also, I attribute this credit to she after these 4 years. Okay, so I will continue my second talk.
Why do you have a blank slide?
Yeah, that's the thing is because
Oh, okay.
yeah, that's for a pause after my first project. So yeah, giving you a rest and thinking about it.
Well, actually, can you go back to the blank slide before that? Don't sit on the blank slide. Sit on this. Let people look at the takeaways.
Oh, okay.
So that they can like spend some time absorbing it.
Okay.
So I think you can take out the blanks.
Yeah, I think.
Yeah.
What you could also do is you could take the takeaway slide, copy it, and then the bottom in red say questions ? And like so you can make a separate thing with like clearly a pause for you, but leave the takeaways on screen.
Okay.
Yeah. Someone's leaving your talk this week. They put their references up as the slide they left afterwards.
Today, right?
Oh, yesterday.
Yes, that was so bad.
Okay.
Yeah. And so during your defense, I would maybe only take 1 or 2 questions because otherwise people might run away with it and then you're like, oh no, I have no time to present my other thing. So say like, all right, I can take 1 or 2 questions.
Oh, okay.
Just so that way it doesn't like continue.
Or like for defense, it's usually like the actual question at the last.
Yeah. Yeah, you don't have to take
It's
them all.
different from like practice. Because we have many things we want to say, but defense is that, oh, this guy is going to graduate.
Okay, so yeah, I will keep this style. So, and I will make the questions in the end of each of my style project, and I will not take any question in the middle of it. So I
You
think
can
that's
take some. Just keep an eye on your time.
Okay.
1 question, perhaps like slide 2 or 3. Very few stuff. The very first few stuff. I think it's 2. Number 2. Okay, so what do you mean number 2?
Number 2.
This is number 3.
Oh, number 2. Okay.
So what do you mean by local time variations?
It's the
Variations in local time?
variations through the local times.
Okay, because local time variation it's not clear is a variation of chemistry or local time.
Just say diurnal variations.
Yeah.
I think he's being silly.
I will say
I think he's being silly. I think nobody's going to be confused by whether the clocks are broken. But
because I already
No, it's not.
said it in my paper, so I think it's okay.
More broad version here. 'Cause I mean, I
Yeah,
was
you don't
like-
have to copy the paper.
I was looking at that and I was like, temporal and local time variation. Both of those are.
Oh, wait,
temporal.
yeah, actually that's
Yeah.
confusing.
Diurnal. Okay.
Yeah, maybe say secular and diurnal or annual or something. What does temporal mean? Long
Or
term?
long-term
years.
variations.
Yeah, I would say long term.
Yeah.
Long-term
You
variations.
can even
It's not
say in
tenure.
parentheses after temporal.
Mm.
Well,
No, just say long term.
yeah, long term variation.
Yeah, actually, you're right.
Or
Technology.
you can say decadal variations if you wanted to be
Oh, yeah.
specific.
Yeah, that's also okay. But I try to avoid that word because we have a decadal decay.
Yeah.
So because I'm not explaining that
This is-
decadal
this is-
decay.
Yeah.
So that's the
Or no, say multi-year.
Uh-huh.
Sorry, say multi-year.
Yeah.
multi-year.
Because
Multi-year.
long term could be millions of years.
Yeah, I think that's right. Okay,
This is good.
Yeah.
Because they visit.
Yeah, this is good.
sure. Okay, I will try.
Time variation is also temporal variation.
Yeah.
Yeah.
I was sitting there for a long time being like, oh god, wait, what?
I mean, local time variation on Venus is not the temporal because it's more like a longitudinal stuff. It's tidal law. It's
Oh,
it's
okay.
so slowly rotating, so it's more like.
But it's like not everyone knows this, right?
Right.
Yeah, you are right.
Even us, like we didn't figure it out.
Yeah.
Okay, yeah.
Okay, next section, because I believe.
Okay. Okay.
Maybe you want to present the ISAT project first.
Oh, that's not a bad idea.
Yeah, you can present the ISAT project first.
Yeah,
Okay,
because
okay.
I'm gonna have to leave.
Yeah, Kobe
Yeah.
is like more familiar with that.
That's a good idea.
Okay.
Sorry to mix you up. I forgot that COVID testing closes earlier.
Oh, okay.
I want to go do that.
Okay, sure. So my second part is mainly about Enceladus. I want to understand the thermal equilibrium and the evolution of ice shear on Enceladus. So first, since the Cassini flyby, we have known that Enceladus is one of the most active one of the most active objects in the solar system, and it has the active plumes which erupted from the south polar terrain. So this makes it that, and also combined with other gravity and libration observations, we may think about this satellite as the subsurface ocean. So if it has the ice shear ocean overlaid on the core structure, we may think about the thermal equilibrium of this satellite and how is this equilibrium is reached. So from our current observations, we know there is a high surface heat flow that is losing on the surface on the ice shear of the Enceladus. So to compensate this heat loss, we need the large amount of heat generation inside this satellite. So right now, the best candidate is the tidal dissipation, but from previous work, we only have the estimates of this dissipation rate at a few gigawatts. So this is not enough to match the surface heat flow, which reaches about over tens of gigawatts. So we want to know what kind of other mechanism can also contribute to this heat generation inside this satellite. Our current question is that what process can produce the sufficient heat to match the observed high surface heat flow? Our hypothesis, the potential answer of us is the forced libration. The forced libration can actually enlarge the amplitude of the libration of the ice shear, which can enhance the heat generation. So what's the forced libration? Optical libration is a company terms that relative to the forced libration. Optical libration means that it's caused by the eccentric orbits by the satellites, which will may have this surface biology move around the surface by the amplitude of 2 eccentricity. The forced libration is caused by the torques from the primary, which can change the rotation rate of the surface of these satellites, and this will increase this at some case will increase the libration amplitude of this body. So this kind of enlargement of amplitude may cause more heat generated in the ice shear. So right now we want to calculate how much heat is increased by this forced librations. And we use a model from Whitehouse in 2013, and which consider the finite elasticity of the ice shear to calculate the libration amplitude. Our model is well accounting for the the viscosity profile in the ice shear, and also we consider different interior models which has different shear thickness, which ranges from 5 to 50 kilometers. Our tidal dissipation calculation is from a simple formula from the Wisdom 2004. And this, I will show you our results. To the left, I will show you the dependency of tidal heating in the ice shear on the shear thickness, or you can say on the interior models. So the dashed line is the tidal dissipation without the forced libration, while the solid line is the tidal dissipation including the forced libration. We can see when the ice shear is very thin, this enlargement of tidal dissipation will be significant. It can reach over 10 gigawatts. The blue regions shows the infrared libration amplitude from the Cassini measurements. And however, even we include this forced libration, the conductive cooling rate is increasing with the thin shear. Is increasing as the shear thins abruptly. So this will also cause our forced libration will not cannot explain the high surface heat flow. So our inference, so our conclusion is that if the Enceladus is in thermal equilibrium, either the heat generation, large heat generation must be happening in the core or in the ocean. And in other case, Enceladus is freezing with time. This heat is this subsurface ocean is just a relic of the history heating events. So another thing that we want to understand is how this forced libration can affect the thermal status of Enceladus ice shear. Previous work shows that if in some case the Enceladus ice shear may go the runaway scenario. So that means if the shear melts, you have a thin shear, which means you have a large amplitude, libration amplitude, which may produce more heat in the ice shear, which melts the shear again, and this will go through a runaway, thermal runaway process. So we can use our model to simply testify whether this scenario is working. So first, I need to clarify in our plots there are two types of thermal equilibriums. First, if this cooling rate and heating rate is dependent on the shear thickness in this way, then this point will be a stable point because you can think of there is a little perturbations on the ice shear. You increase this ice shear by a little, and then the heating rate will be larger than the cooling rate. That means your shear will melt again and return to its original equilibrium point. So this point is a stable point. Another case is that if the cooling rate increases, if the cooling rate is not as strong as the heating rate dependent on the ice shear thickness, you will have an unstable point. That means if you perturbate by a little, it will go through the runaway process. So our model can simulate the heating tidal dissipation with different eccentricities and different viscosity configurations. So I will show you here that with the heating rate as the red lines and the cooling rate as the blue lines, the different red lines means the different eccentricities. So here I show you there is a stable point around the 20 kilometers and an unstable point around the a few kilometers of the ice shear. And this in this says that these unstable points can cause the runaway scenario, but the configurations here is too extreme. It requires very thin ice shear and also high eccentricity. We do not think this scenario is likely to happen. And for another point, thermal equilibrium point, the stable equilibrium point happens around 20 kilometers shear thickness, which is in the range of current observations. And this scenario is likely to happen. And so we think this stable point could be the thermal equilibrium in the recent history of Enceladus. So, okay, so I leave this page blank because I want to add some Enceladus missions, but I haven't checked the decadal survey of that, so I need to add this later. Yeah, and okay, so that's the end of my Enceladus work. So to conclude, our libration model can give us the extra heating generation in the ice shear, but this kind of enlargement of tidal dissipation is still not enough to explain the observations. So that says that either Enceladus has a large heat generation in the core of the ocean, or Enceladus is freezing with time. So, and we used our model to explore the thermal runaway scenario of Enceladus, and we found that Enceladus is more likely to stay in a stable equilibrium, which is resisting small perturbations. Our simulation results does not support the runaway scenario or episodic heating events in the history of Enceladus. But our model is not well coupled. It's not well coupling the thermal evolution and the orbital evolution. So this may be a potential directions for our future work. So that's the end of my Enceladus work.
Cool. I have a couple of questions.
Okay.
But that was great.
Thank you.
Can you go back one slide? Yeah. Why is the cooling rate not linear with thickness? I would expect it to be linear.
Why is it linear?
Because you have, I said, like, you have the surface temperature that's pinned, and the shell bottom temperature is pinned, and the flux is linearly proportional to the gradient.
Yeah, flux.
So like your gradient just gets a little like linearly steeper.
But d is in the numerator, in the denominator.
So like the thermal gradient is the
thermal gradient is inversely proportional to the thickness. So this cooling rate is inversely proportional.
Okay, cool. Thank you. More questions. Other people can also jump in. Well, actually, no, she does this. Can you go to slide 26
about this?
26.
Oh, okay, go ahead.
Yeah. So
Oh,
yeah, sorry. So I see there's a tidal heating with 3 eccentricity.
that's right.
So this has happened in the history.
Yeah.
Okay, so there could be like 3 times of eccentricity.
Yeah.
Okay.
From robots and
But I think
world.
this should be stated more clear.
Just say it out
It's
loud.
just exploration of parameter space.
But people will ask, like, you know, the eccentricity of it.
Yeah.
Okay.
Just say like it could have been higher.
Yeah, it could be higher.
Okay.
Also, can you it might be hard, but can you try to label the curves E, 2E, and 3E, or color code them or something? This pattern it's really hard to tell which one is 1E and which one is 3E.
You mean separate the lines?
Either change the colors more,
change the color.
or just put the label them. So like right here, you could put E, and here you put 2E, and here you put 3E. Okay. Whatever feels less noisy to you or less messy. But it's hard to tell which is which.
I think using different colors.
Yeah, I think colors.
Okay.
Yeah, like a rainbow. Of course, they are going to be different. Yeah.
Okay.
Can you go to slide 26 when you're done? Yeah.
Okay. 26, 26, 28, 27, 26.
Oh, actually, no, you answered my question. Let's go to 27 and 28.
28.
Both of them. So it's hard to. So you label 0 degrees, which is good, but it's hard to stop that. What I think could be cool is so like on like slide 2. Can you go to like slide 2? All the way back.
Oh, slide 2?
Yeah, or maybe 2. The second one.
Second slide 2.
This is cool. What do you take this picture? Now go back to 27.
Oh, I understand.
Instead of a white circle.
Because the problem is that the Enceladus looks like Saturn, and Saturn looks like
that's true too.
That's fine. That's the time out.
No, it's
I have to see the text.
But the point is, if you put the little picture here, people will see that it's not rotating, and then you put it here, people will see that it is rotating, and like rotate it. Because it's hard to tell, like, oh, so this is the prime meridian. That takes like, especially if I'm not like I'm a planetary scientist. I do IC satellites, and this still confuses me. If you're not a planetary scientist, they're gonna think this is physical vibration.
Okay.
So I think if you put a picture of Enceladus, and so they can see it doesn't rotate, and then on the next one, you rotate it, and they'll see it's rotating. So really anything that's not a blank circle, anything that you can tell it's an orientation, but I think the picture of Enceladus is the way to go.
And also maybe you want to draw an arrow to say that this is a bulk. This is the bulk, whatever bulk you like creates the tidal heat, right? Is it better? I'm pretty sure like for people like don't study, are not familiar with tides, it could be you get confused.
Well, he kind of says that.
Okay.
Oh, also, so do you understand what I mean about the picture rotating?
Yeah, I understand that.
I think
it's
that
just like a brain as animation. I know that.
What would also be useful here, I think, is if you cover these up with white boxes, show only this, and then remove the white boxes so people can see that it's time evolution. Oh, sorry. So you cover these up and you like show this, and you say Enceladus has a bulge oriented towards Saturn. This is the prime meridian, and then you show this, and you say as it orbits, Saturn appears to move, the bulge moves, Enceladus doesn't rotate. And then you show this, and you say as Saturn continues to move, the bulge moves back.
Oh, got it.
So like show one at a time.
Got it.
So people understand the time evolution.
Yeah, this may be too much information. Yeah.
Yeah, it just helps to like give people information slowly. But I think the picture of Enceladus or something that you like what Brennan does, that would work too. Anything so you can tell like rotation or not rotation. Because this looks like rotation.
Yeah, I will try to do that. Yeah. I very admire the animations of.
You can ask Brennan for help. Brennan would love to help. And I would like, in the office.
I can do my survey.
Yeah.
Anyway, I needed to do it maybe in the future.
And I have a question about this for you. So if you compare 27 and 28, if you move to 28,
okay.
So there will be a 2e plus 1.5 degree. What does it mean?
1.5 degrees for the liberation amplitude.
The optical vibration, yeah.
Okay, so E is the eccentricity.
Yeah, 2e is still optical liberation. You can draw a line here. This one is the optical liberation, and this one is the photo liberation.
But eccentricity, it doesn't have a unit.
Yeah, the units don't match.
Unit?
Eccentricity doesn't have a unit. You show 1.5 degree, but how could you?
It's just to the degree. You can translate it into the radians. That's totally okay.
But eccentricity is also not in radians.
Huh? Yeah, but you probably get away with it.
I don't quite understand.
Exactly, there is a non-unitalist,
but
is also non-unitalist.
I hate that.
Wow.
That's what's in Harvard.
I
They got
hate
away
that
with
so
publishing.
much. There's like a secret small little part. Yeah, you're fine. Somebody might ask.
Okay. Anyway, if I can draw by myself, I will draw by myself. Okay.
That's so bad. It's not your fault at all.
Okay.
That's like
It's
nature's
just
fault.
it's just
Like
this
the-
parable has concluded this, so it's easy to take it.
Yeah. I hate
But
reading.
if you take any picture from the other's work, you have to know the meaning of each.
That's
part.
right.
Yeah.
Yeah, that's right. And I understand.
Like for me, why eccentricity is a degree at it. Doesn't make sense. Makes sense
It's
to me
just
anyway.
it's just a non-unitary. So when you calculate this, it's has the amplitude of 2 times the
I think
eccentricity.
you want to be more
Mm.
like clarify that E is eccentricity here when you show this figure.
Okay.
I don't know
Yeah.
that you ever state that.
Yeah.
That would really help.
I said in the previous slides, I think, in,
Okay, just make sure you
optical light,
Yeah.
I said the optical liberation usually has the optical liberation has the amplitude of 2 times eccentricity.
Okay.
So
Because this one was actually not very obvious to me, and I first thought, is it
Anyway, okay.
Something like that.
I'll get rid of this picture. I'll draw by myself.
I'm gonna go. I will watch the recording. It's on YouTube, right? So
Yeah,
I can
yeah,
watch
yeah,
it?
yeah.
Cool. So I will watch the recording and talk about the last part.
Okay.
Sorry.
You know, the link is in my email. I
Yeah.
sent it yesterday.
Cool. If I can't find it, I'll ask you. Cool.
And also, that was science question. So, did you go to Wencheng's talk?
Why?
Wencheng's talk? He talked about Enceladus shell and why it's like has a
Oh,
symmetry
yes,
of
yes.
the shell.
Hmm.
What do you think about her work? I mean, it's very similar, right? She is trying to explain why Europa doesn't have a plume. I mean, Enceladus has a plume, and also why Enceladus is like you have a plume at a certain hemisphere.
I can only remember her work about the asymmetry between the solar poles and the north polar. Why is the solar polar has the has the
It's something to do with
plumes?
size.
Yeah, that I only can remember her work about that. But about the Europe and Enceladus, I think that work is still ongoing. So I'm not sure.
Published on PNAS.
Oh, it's already
You should
okay.
check the paper. If the committee member is going to, will ask you afterwards.
Okay, I will check it out. Yeah. Okay. So, yeah, actually, about her the work about the Enceladus and Europe, I do not know what's the takeaway.
Okay.
Yeah.
So why it happens on a certain place of Enceladus?
From her work, it says it's just the
Just
from me.
from yours.
From me, I don't know. Yeah, I do not explain the asymmetry between the south pole and the north pole. Yeah. Yeah, my model is totally symmetric. If it's just a 1D model, so it's just the average shear thickness I'm concerned about average tidal dispersion in the ice shear. So I do not consider the latitudinal variations of this ice shear thickness. So yeah, I will check that paper. Okay.
I think the energy balance in the ocean also affect your boundary condition. Like how much heat you can get from the ocean.
Yeah,
from meteor.
we do not calculate the heat generation in the ocean. The boundary conditions is just a very simple boundary condition. I take the temperature at the bottom of the ice shear as always 0 degrees. So it's a melting temperature. I do not consider the salty the salt in the ocean. So I do not consider that.
But you need to have the input of the heat flux at the lower boundary.
Input of heat flux is just in most of our work we only calculate the tidal dispersion in the ice shear, and when we consider the thermal evolution of Enceladus, we add a fixed flux thermal heat flux to the ice shear bottom to represent some heat generation mechanism in the ocean or in the ice in the core. So that's our methodology. So we actually do not know how this heat is generated.
So talk about forced librations. So it generates some heat, right? And where do we input this heat?
Oh,
how do you treat this heat? Is a lower boundary from the lower boundary, or is something anywhere? I just wanna...
it's just from a simple formula from Wisdom's paper. Wisdom's paper has a formula. Okay, I will add this backup slide later.
Physically, like, how does forced elaborations heat the shell?
Oh, okay. So you can think about it's like friction between different viscous layers.
Oh, so it happens in the
ice shell. Yeah, if your ice shell has a surface amplitude very large, this friction maybe do a lot of work.
Okay.
So, yeah.
So it's something in the shell.
Yeah.
All right. I think this is important to tell people. Because
okay.
If I think about the
I was thinking about that,
like, it stretched the entire planet because I don't really know the forced elaborations.
Okay.
I think you need to explain the forced elaborations more and how does it affect the heat energy budget in the ice shell.
Okay. Okay.
I just seeing this figure, I was like, oh god, I remember reading that.
What do you read? What do you read this paper for?
My first project with Francis was actually on cryovolcanism on Europa.
Okay.
And Terry also does Europa stuff.
Okay.
It's like, oh god, I remember this. I remember why I quit that project.
Yeah, Terry's paper, I think
He makes good papers.
it's a good paper, and I really like he wrote down the detailed mathematics in appendix, so that's very good.
Yeah, could you go to the first slide?
First?
Oh, that is a different one. Whatever.
Okay, so
just go ahead.
Okay, let's go to my Venus 2D. Okay, so after I studied the temporal variations of chemical species on Venus, I'm starting to think the mechanism that controls the spatial variations of these chemical species. So Venus is so special that it is so slowly rotating. So that means its day side is more subject to the sunlight. So this may cause the large day-night difference around the latitudinal circle. So here I am thinking about the mechanisms that control the local time variations of chemical species. So the local time means because Enceladus because Venus is slowly rotating. So local time, you can think about local time variations as the longitudinal variations. Okay, so I show you the two observations. One on the left, the observations is from a ground-based instrument. On the right, you have the observations from Venus Express. And these two observations both show us there are some peaks around the terminators. This two peak feature is the feature that I want to study for the sulfur dioxide local time distribution. So my question is, what controls these two peak feature in the local time distributions of sulfur dioxide? Is it dynamics as I shown on the left? It may related to the retrograde super rotational flow, abbreviated as RSZ, or the subsolar antisolar circulation, abbreviated as the SSAS, or it is the photochemistry accounting for this local time distribution. This which involves the carbon, sulfur, and chlorine species. So to answer this question, I used a 2D chemical model combined with a 3D dynamic model to do this. My 2D chemical model is basically the extension of my previous kinetics model, and I extended it in the longitudinal dimension. And then this 2D chemical model will need the output of wind and temperature fields from a general circulation model, and this will drive the advection of chemical species in my chemical model. And finally, my model can output this two-dimensional chemical distributions in a longitude pressure plane. So first, after I developed this model, I compared my simulation results with observations to validate our model. Our model is basically consistent with the current available observations for the species like sulfur dioxide, sulfur monoxide, and OCS. So this gives us confidence of the accuracy of our model. And then I used my model to study the sulfur dioxide local time distribution around the cloud top. So I plotted the error bars as the blue error bars. I plotted the observations as the blue error bars here, and also my simulations as the solid lines. So in the second row of this plot, I show you our model can well simulate the two peak features of sulfur dioxide local distribution. And maybe I should remove this. Okay. So and also show your wind field for the vertical and horizontal wind field in the first and the third rows. So this is from, oh my God. Sorry, my battery is how do I?
Yeah.
My battery is dying.
Yeah.
Oh no.
No.
Do you have a charger?
Yeah, in my office. I wait for a second.
Used to put this side or that side on.
I think so too. The two comments that I had were how slow is slow, like how long is the day?
Yeah.
And then I don't know if this is actually a good comment, but I was thinking having a figure showing what local time means. Like,
Yeah, that's right.
Like have Venus, have little sign say like this is noon, this is midnight.
Yeah.
Just he says it, but I feel like people are gonna miss that.
Yeah. And also, do I think it's better to introduce the Venus in general at least? I think it's useful.
Yeah, there's a lemon under here. That's disgusting. Yeah, I think he could probably do. I don't know what about Venus would be good to discuss. So, like, he doesn't need to say everything.
That's right.
But I think that
You should tell people like that is totally locked. Or
Venus is totally locked.
no. Well, it's kind of like,
I think that the figure that Kobe was offering to make for him, I think that would help out a lot.
Yeah,
So
yeah.
you could show like, this is how thick the atmosphere is. This is the different parts.
Yeah.
This is what we care about.
and also a daytime, like how much is
Yeah.
orbital period?
What is Venus's day like?
I think it's 200 days.
It's a lot.
It's kind of like totally long. But you're right. It's not. It's
like,
not,
it's not
really.
perfectly, but it's almost. Yeah. I haven't thought about how slow.
Oh, that's fast.
I don't expect it. It's so power consuming. Maybe it's just
Is it a new laptop?
Yeah. So maybe it's just because I opened the Zoom.
Yeah,
Oh,
Zoom is very
yeah.
energy consuming.
Yeah.
And also YouTube. Okay.
It's lazy.
My YouTuber is still working, right? Okay. I can be a VTuber. Okay. Let me have a rest.
Yeah, take a breath.
Yeah, we can talk about some.
Sure.
We have some suggestions. Like, it's better to show something like saying this is a night, this is the daytime.
Yeah.
Because local time doesn't mean anything to us.
Okay.
Right. So if you like have Venus and like a little sun over here, so you can say like this is noon, this is midnight.
Now, how long is the day on Venus? 200 days, right?
So that depends on which day are you thinking. The sidereal day is 224 days, and that means you use a fixed point in the universe. So if you think about solar day, it's 117 days.
Okay.
Yeah.
So what do you mean by 24 hours?
It's just the scaled the longitude.
Okay.
Scale the longitude to the local time hours.
That you have to explain.
Yeah.
Because otherwise people will think that, oh, 24 hours on Venus.
And then it's not a story.
Okay.
So yeah, I think having a figure that shows like, you know, this is what noon means. So this is longitude, and this is what midnight means, and this is 6 p.m. or something.
That's why when you say something like local time, I think it's not better. I think it's better to say something like longitude.
Yeah.
Yeah, but I know you mean like it's not really longitude, right? It's like
Yeah, maybe I can replot, remake this plot just using longitude to
because you have to.
Yeah.
There's something like when you present to some people like you don't understand anything about Venus.
That's right.
How do they think when they say they're 24 hours out?
We can.
And when you introduce it and say, like when you say Venus is a slow rotator, say how long it takes.
Okay.
Because I was like, oh yeah, I don't actually know how long it takes, and then Fabio was like 200 days, and I was like, like people are gonna be like, whoa, okay. So it always helps.
Okay.
People cannot keep every number in their head.
Okay.
And also maybe you can say something like this. So for example, you say, put a number, like a water number. This is 6, 9, 12, 15, 18. It's not useful. And also if you move to this figure.
Okay.
I think it's better to have some like 2 lines. I say, oh, this is.
Oh, okay.
That is nice.
Yeah.
That is going to be useful. And we can understand what does it mean.
Right.
So I feel like, is it in total that is 24 hours?
Which one?
Like the entire local time that is like from 0 to 24.
You mean this one?
Yeah, the x-axis, the range of the x-axis.
Yeah, it's from 20. You can plot the 24.
That is a bad.
23 to 0.
That are bad picks.
They almost look like they're like getting larger. The further
Yeah, you don't know the largest one. I think it's better to do something like 0, 6, 12, 18, 24, right?
Yeah.
This is terrible. What is the largest one?
Yeah, I think.
That looks like it's someone else's figure though, so maybe
Yeah,
you
yeah.
can't change
This
that.
one is like that. Not like that. Maybe this is just a.
Yeah, I mean, I believe it. It's just it looks kind of strange.
And also, it's better to have some arrow say, this is a peak. This is a peak. Yeah.
Okay.
Because when I say peaks, we have to find it, right?
Yeah.
But if you just point them out on the slide,
That's right.
it's easier for audience. Because it's a 1 hour talk.
That's right. Okay.
You have to do like some babysitting for audience.
All right. Already. recovered my breath. Okay, so I used my model to simulate the local time distribution of sulfur dioxide around the cloud top, and I found that our model can well simulate the two peak feature around the terminators for the sulfur dioxide. So you can see this feature in the second row of this plot, which shows the two peaks located around the terminators. And from our model, this feature is produced by the dynamics. The third row, the first and the third rows shows the vertical and the horizontal winds. And from this wind analysis, we can find that the semi-diagonal tides will explain the two peak features, while the retrograde zonal flow will explain the positions of these peaks. So that means that semi-diagonal tides has two upwelling branches, will bring the sulfur dioxide rich atmosphere upward to the cloud top. And this will cause two peaks of sulfur dioxide. And then the westward super rotational flow will shift this peak toward the terminators. So that's why we get this kind of feature. Okay, so that is the sulfur dioxide local time distribution around the cloud top, and then we studied the sulfur dioxide in the upper mesosphere. You can say around 95 kilometers. So for this sulfur dioxide feature, we found that both the photochemistry and the dynamics will contribute to this local time distribution. So around the 95 kilometers, we have the subsolar and solar circulation, which is just the day-night transport horizontal flows, and this will bring the sulfur dioxide rich atmosphere on the night side, but on the day side, because we have the strong photolysis of sulfur dioxide, which will dissociate the sulfur dioxide into sulfur monoxide and oxygen atoms. So this will cause we have lower sulfur dioxide mixing ratios on the day side. So both of these will explain these two processes will explain the sulfur dioxide day and night difference. I will also put a day-night here. Okay, and except for besides sulfur dioxide, we also studied other species. The carbon monoxide is currently also has a few observations from Venus Express. From our model, I show you the 2D distributions of sulfur monoxide in the unit of ppm. The color here is the sulfur monoxide mixing ratios. Horizontal axis is the local time of Venus, and the vertical axis is the altitude. So here, the sulfur, carbon monoxide is basically a long-term species which will be distributed very uniformly over this 2D space. And our model can also explain the terminator difference that was observed by the Venus Express. Basically, this bluish this is cyan. Okay. This cyan lines and red lines, this difference and this reverse of these two differences can be explained by the subsolar and solar circulation and the transition regime wind structure on Venus. So, except as well as carbon monoxide, we also we can also simulate our model can also output the 2D distributions of other species like water, chlorine, hydrogen chloride, and the OCS. So this species, unfortunately, we do not have too many observations for this species, and so our simulations can be a good predictions for future Venus missions, especially for the future Venus. We have 3 missions incoming: Veritas, Invasion, and the Defensive Plus. These 3 missions will tell us more about the tracer variabilities in the Venus atmosphere. And also we can use these tracer variabilities to infer information in the low atmosphere and even on the surface, like volcanism, or we can use it to study the Venus habitability. So our model will guide these future observations, future missions to more accurately interpret the observations. So for our Venus 2D work, the main takeaways is that the dynamics and the photochemistry, the 2 processes compete with each other and the controls the local time distributions of chemical species in the middle atmosphere of Venus. The sulfur dioxide around the cloud top is controlled by dynamics mainly, and in the upper mesosphere is controlled by both the photolysis and the subsolar antisolar circulation. And for the carbon monoxide, which is the long-term species, it will have the features that can reflect the circulation pattern in the upper mesosphere. For other species, we make predictions which can be tested by future missions. Okay, so that's enough for my 2D work, and thank you.
I have a basic question. What does RSZ stand for?
Oh yeah, maybe I should not use that. Retrograde super rotational flow. Okay. Zonal flow. Yeah. So it's just the super rotation you can think about. With the word super rotation. Yeah, that's
I think
not.
I have a few steps. So we're gonna put a science question.
Okay.
I don't know you have done this before. So so the first suggestion that you have, so you have 2D wind field, right? So it's better to present the 2D wind field to people at first.
Okay.
Because you are talking about the transport, and I think in the middle you talked about the vertical transport.
I do not have a backup slide. Yeah, okay, I will put that. I'm gonna.
I think it's better to put them in the introduction part.
Introduction.
Yeah, okay. Like the second slide or
maybe this one.
And also try not to use the abbreviations.
Okay.
Yeah, that's especially when like for people who don't study atmosphere, they don't really know the meaning of retrograde and
that's it. Yeah. Okay.
And that is a big question. It's like it really confuses people.
I will try to avoid the use.
And you can like walk into this project by saying like from the first one, your first project is a long-term study, it's a 1D study. But on Venus, there is a strong superrotation and has a very complicated circulations. When you have circulations, you will transport the chemical species from the day side to the night side. And in the day side and night side, there will be a difference about the photochemistry, something like this. So you can start from this to introduce why do you want to do a 2D simulation, because you want to connect to those things.
That's right. Yeah.
For as a physics difference, right? So it's like you have to make some connections with your.
Yeah, I'm still thinking about how to connect the 1D and 2D. That's the logic there are not very clear. I was thinking about that.
Yeah, I think the point is like is something that photochemistry is important. So
dynamics.
So photochemistry is not important.
It's in some regions that it is important, but dynamics is so. In fact, in my paper review, And some reviewer says that, oh, you cannot say the dynamics is important because photochemistry also plays a role. So finally, I compromised and said both photochemistry and dynamics play important roles. So that's
did you study the difference, like which one is more important?
That's the things I did not study. So quantitatively to discriminate the two effects is so difficult. So on my paper, I only studied which one dominates. It's very apparently dominates. It's like I plotted the time scale for the dynamics and the chemicals, and this can be approximation for my which one is dominant. So basically, you can see from I have shown this plot. So basically, you can see the red is the chemistry dominant, and the blue is the dynamics dominant. For the sulfur dioxide, around the cloud top, you can see the both are important, but for the two peak features.
You have this.
Yeah, for the two peak features, it's mainly dynamics dominant.
Okay.
And on the upper atmosphere, the radar is become significant. So that's the chemistry dominant. But on the night side, you do not have photochemistry. Then I can say it's mainly dominant.
So they are both important.
They are both important
I think you can really state this fact because like in the 1D simulation is just you only have photochemistry. You have no transport.
No.
So you can say, all right, so. And you can introduce this like by saying we have like 90%, 95% of the audience have barely zero knowledge about the wind on Venus.
Okay.
They don't know there is a super rotation. Like what is super rotation? You have to define. Like the wind, for example, the planet rotates like in 200 days. The wind rotates the planet in just 4 days. Right?
Yeah, I'm thinking about.
You should say that because I did not know that.
Yeah, right.
Okay.
Because there are so many things that audience will never know. So it will really hard for them to process many information.
That's a
lot of information.
I'm thinking about this plot is very nitty, so I maybe can use this.
We should put it at the second slide or the first one.
Yeah. Around the cloud we have super rotation, and in the upper mesosphere we have this solar.
Yeah, and it's better to not use abbreviations like MT, ET. What is that? ET is this aliens or something.
That's even your
And also, what is N, right?
It's just the direction. Yeah.
Oh, okay. Because people will think, oh, is that night side or something? Yeah, this is kind of like not very good.
I looked at it and it was like mountain time, Eastern time.
Oh, this maybe the North Pole. I'm not sure, but this maybe not.
Just to avoid any abbreviations.
Yeah.
You just tell people like what are they.
Okay. I can draw it by myself. It's
so
not difficult.
I think you have to spend more time on introduction.
Okay.
Because introduce the wind field is really hard.
Okay.
So this is I think this is a
maybe around this one.
Yeah, if you introduce the dynamics very well, I think you can. I think the other parts are good.
Okay.
Because it's not obvious that the wind can go to support.
Right, yeah.
Okay.
Can you go? I think it's slide 19. Yeah. So, okay. So you talk about how you match the two peaks, and I actually got really confused there because in the observations, the peaks are actually not.
You mean this?
Yeah, like that guy, and then even the one on the other side too.
Good question. So we only match the rough peak of this. That is we do not know, but it can be caused by the small scale dynamics like waves. So that's the stuff our model cannot simulate. Our model is a very low resolution model. So it has
I would say that just because people are gonna be like, but what are those other things? Just say like these are, we're looking at the long-term variations or the long wavelength stuff.
Yeah.
And that makes sense.
Okay.
And I think you introduced a new word here. What is a terminator position?
Yeah, no one's gonna know what that means.
Terminator.
The position
Oh,
that Terminator T800 comes in.
It's where you go from the day side to night
Yeah,
side.
yeah.
Oh, okay.
So that's why I use this. This around 6.
So the same with the night side and night side and day side, you can just like draw an arrow, say this is the Terminator position.
Yeah.
Yeah, we can understand
Yeah.
what is the meaning of this.
Yeah, arrow.
And directly give a definition for Terminator, because everyone's gonna be like, oh, the movie.
I think also
the movie.
Yeah.
Oh,
yeah,
okay. Yeah, that's a good.
we have an invasion of boys. So I think it's better not to say that we fixed the observation, because it doesn't really fit into the observation, right?
Oh, you can. You
I think
mean
you
say
can-
some more conservatively?
I think you can say that from our simulation, we can kind of explain the trend in observation. I think that is better.
Yeah.
Mm.
Yeah.
Yeah, that is a
that's
less
not-
strong statement.
I like the word trend because it that
Oh.
shows that I'm not fitting all of the data.
Yeah.
I'm fitting the important parts of the data. Yeah.
I think I will say the local time pattern. China is not a good word here because it's a space distribution. China is more like a temporal stuff. Yeah.
Okay.
Yeah.
And I have a question about your observation.
Mhm.
So how do you observe, like, how do you achieve those, like, let me think how to explain this. So Venus is very slow rotating, right?
Mhm.
And to get the observation of each point on the planet
Mhm.
in longitude,
Mhm.
how much time do you need to achieve the global value?
It's actually it's a ground-based observation.
Yeah.
So it can observe the whole disk of this Venus.
No, but you can only observe the
Yeah, you can
one
only
side,
observe the
right?
side that's facing
What about the other side? It's not on your
This
on the back.
10 years observations. So basically,
But you said that there is a faster rotation. There's a super rotation. Super rotation. So if it's a long time observation, those tracers are transported away from the local place.
mhm.
And how do you say that this is the? I don't understand. Like when you say local time is
It's just fixed to the surface point.
fixed to a surface point.
Relatively to a fixed surface point. It's just
like a particular longitude.
yeah, you can say that.
Which I have something wrong. So yeah, I'm really curious about this. All right, so let's say this is the Earth, this is Venus.
Mhm.
So what you can observe is something like at here, right?
Mhm.
And this entire disk. And so you say this is a disk that you can observe.
Mhm.
All right, so you can get the point here, 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 here.
Mhm.
But Venus is very slow rotating.
Mhm.
If you want to observe here, you either have to wait this stupid thing to here.
Mhm.
That is like after 1 year, right? After like
I have
a few months. Right.
I'm not sure,
So
but
are these all average points over
Yeah.
like the 10 years?
yeah, all average point. So if you have the observations at the local time, it's you can average that, but it should be at least have some points for one local time grand longitude, I think. So it's 10 years observations. I think it covers almost all the local time regions. So
Still don't understand the local time. So
the local time,
still
it's just the
no listen. So you can observe here, right? And then if you want to, let's say this is the sun. This is the sun. So this is your day sun. This is your night sun.
right now you can observe from night side local times. So
Yeah.
okay.
But if you move to, so you have to wait Venus to move.
Yeah.
And move to here, you can see the day side.
That's right.
But it has a super rotation. Every species has been transported to the back.
We do not consider super rotation. We do not consider the rotation of atmosphere. We only consider the surface rotation. That's you can see.
But you have transport. You have. So
I know there's a transport, but we still consider whether arrow is a transport to where, but this point is still local time. So it's still local time to,
But
it's a fixed local time.
It's a different local time now, though. So, because I just realized I was thinking about this wrong. Okay, so here's your sun. This is midnight. This is no longer midnight, or this is midnight, but we were okay. So midnight, we rotate. This is no longer midnight. This is midnight now.
Yeah, it's a midnight is.
So it's not a particular longitude, like I was saying.
So it's a particular time.
Yes. It's a particular amount of shade, I guess, that you're.
Yeah.
That's
midnight.
that's.
It's always going to be incomplete darkness.
Yes.
I think you really have to explain that.
Nah, that's too complicated for the I will know.
But everyone will be confused.
I'll try to use longitude.
Don't use longitude. Don't use longitude. So I think the best way is that you have. I think you can start from something like. So people's understanding about Venus is from looking them into the sky, and you can say that Venus has the same face with the moon. And you can say that this face is kind of like the midnight. That face is kind of like the.
All right, hang on, I'm putting you on the speaker. There we go.
There's a slight delay. This whole I don't think this is that confusing. Can you just put in parentheses below Venus local time? If you took an Earth sundial and put it on Venus, this is what it would read.
Sorry, what do you suggest?
Yeah, could you repeat it, Kobe? Sorry.
So like, what local time right here means is if you use like a sundial from Earth, this is the time it would say. It's like. I don't think this is a confusing concept.
I think if you just call it call 24 midnight or something, people will understand like, oh, this is midnight, and so midnight is kind of going to be changing, but it's always.
This is that the union is the.
Yeah, I like that.
Yeah,
that is good.
That made a lot of sense. Just calling it midnight.
Okay, got it.
Yeah.
Also labels
Yeah.
Levels what?
solar noon.
Solar moon.
Oh, solar.
Noon, just noon.
Oh, noon.
Yeah.
Okay.
Moon.
Okay, levels noon and midnight. Okay, levels noon and midnight.
I think for defense talk, you want to make everything easy to understand.
Yeah, it's for a general
It
audience.
is for general audience. It's like for high school students. That kind of level.
Yeah.
Because I have attended a lot of good defense talk in Caltech, and they just do for high school level.
Okay.
Although they have complex mathematical equations everywhere,
Right.
just avoid them.
Okay. That's good.
Yeah, I think calling it noon and midnight will help.
Yeah.
Yeah, maybe I just remove those numbers and just plot midnights.
I think it's okay to leave the numbers, but if you just draw a line saying this is nighttime and then this is midnight, this is noon.
Okay.
Yeah, I think that will help out a lot.
Yeah. Because for Jupiter, it has many stupid longitudinal systems, like longitudinal system 3, longitudinal system 2, longitudinal. Just tell them this is a different location on Jupiter, and it's fixed by the magnetic field, and that's it.
Yeah.
So you can think there is a subject.
just a different reference point.
Yeah.
Yeah.
I think that's a maze of planetary science. I mean.
Yeah. So right now you use many jargons just in your field.
Okay.
And it's you can think for example, Zach come to you, and he see the local time. He think about
Earth.
yeah, the local time here. This is 16, right? Something like this. You lost her.
That's okay.
Yeah.
That's true, actually. If you wanted to make it even more obvious, instead of 5, 10, 15, 20, you could do the normal time where it's 5:00, 10:00.
Yeah, Rachel has said about that. I'm thinking about that. Yeah.
12, 0, 6, 12, 18, 24. Don't do 10, 20. No, that's it.
Okay. Sure.
For lunch. Anyway, I think the others.
What?
You can just cover up the 2015, 10 with a white box.
Oh.
And then put 24,
Got it. Okay.
18.
But you can remake.
Yeah, I can remake it. I think I have. It's not.
Because there will be ticks.
Oh, yeah.
Problematic.
But yeah, I think Hua's suggestion of doing a little bit more background will help. Or just like
Okay.
introduction.
Okay. Yeah, when things go to the multi-dimension, it will be so complicated.
I think you showed the 2D wind field in your candidacy oral example, right?
No, I think.
You have that. Do you have that?
Yeah.
Outside?
I think I'll show it.
I'm pretty sure I see some.
That's right.
Something from yours.
I showed it maybe in some conference. I forgot which conference. Maybe you know that.
I think you can put the wind field there, like the zone of wind.
It would help people understand what you mean by 2D.
Yeah.
Just be like, this is what the
Yeah.
model looks like.
The 2D, do you mean the height and latitude or longitude and latitude?
Yeah, longitude and pressure.
If you have your, is this your
figure.
status?
Yeah, this is my thesis. Let's see. Where is my figure one? Okay, just a figure 2.1. And oh, here, yeah. In fact, I have the second plot. The second plot is overlaid by this node.
Do you have a wind field?
Yeah, second plot has the wind field, but not too clear. Yeah. It's the wind field.
This is the x-axis, y-axis. Height.
Yeah, y-axis is the height, local time on x-axis, and
So which latitude is this?
so this local time you can.
But this is vertical.
Oh, this is average stuff.
Is this vertical velocity?
You have this is just the wind field. The color is vertical velocity, and this vectors are the wind.
Oh.
Vectors. I'm saying
But
vectors.
you have no scale about the vector, right?
I
I mean, that's
scaled.
on this figure.
I scaled. It's already.
No, I mean the scale means that how long
Oh.
is 1 meter per second or 100
Yeah, I
meters.
removed that because it's so confusing in my paper review. I originally had that, but it's so confusing.
I think do you have anything that is a cross section of like the latitude and longitude? The latitude and height. Because it's a pretty zonal, right?
This is only 2D. Why I have latitude across it? This
So
is only
what is it? So you 2D.
Oh, you mean the 3D design?
What do you mean by 2D?
I mean 2D longitude pressure. This is
Longitude and pressure.
it's only 2D.
So assume it is the same for different latitude.
It's in fact I integrate the tracer transport equation. It's a kind of yeah. So for this tracer transport equation, I integrate it and until I get the final until I get the C other equation is the Mardinoli not Mardinoli.
So you get a stream function from this.
Yeah, it's like a stream function.
Yeah. Okay.
So we do not have latitude and stuff.
Okay. I think you want to explain like 2D wind field. Like, I think it's better to show a figure. Like, what kind of 2D wind field are you using?
Okay. I was
Because otherwise we have no idea about like what is 2D wind field.
okay. I will show it here.
And also, so I think in
But I can draw a very simple cartoon of the wind field.
Cartoons are great.
Yeah.
Because then people don't have to be like, oh god, this is the science, and you're just like, this is just what's happening.
And also-
okay.
Yeah, you have to specify like the axis of 2D. Is in
Yeah, and when you say pressure, that's that's the
Height.
same as like height, right?
Okay. Yeah.
you know, see, not everyone study atmosphere.
Right, because like when you said 2D and the pressure, I was like, that feels wrong, but I know that that's like what it is.
Okay,
But
okay.
it's just that pressure changes with height.
Okay, I will try to use the altitude all the times. Oh, altitude?
I think it's okay to say pressure, but just say pressure which changes with altitude.
Okay.
Number 19.
19.
So you said something about the transport.
Mm-hmm.
Do you think it's better to show stream function, mass stream function?
I do not have that. I do not show that in my paper. Yeah.
You don't have that in your paper?
No.
Interesting. The reviewer didn't ask you about
No.
it.
No, I didn't thought that function. Yeah.
Interesting.
In fact, when I do the calculations, I directly use the window to calculate. I do not use stream function to calculate.
Well, how do you know that is a contribution? Like, how do you know the circulation pattern?
Circulation pattern is just from 3D GCM. Yeah.
But you need a stream function, right?
Do I need? I mean, you can use the stream function to calculate the tracer transport, but you do not necessarily need that. You can.
But if you don't show the stream function, it's really hard to visually accept that it is caused by the transport. Because you have so many things going on.
Maybe you're right. Yeah. So that's the stuff of a paper. Yeah, maybe using a stream function is more easier to understand that.
Yes. Because wind field, you have to integrate the wind field to get a stream function. The wind field itself is really hard to understand.
Do you think a wind zero is still?
I'm gonna be honest, I don't know what you guys are talking about.
It's my personal opinion. I just don't understand. Like I think you said something like it's a transport from the deep atmosphere and something like this, right? I think the stream function could be very useful.
Yeah, stream function is very useful.
Down at here.
Oh, okay. A plot would be nice.
Yeah. A plot like showing how a transport that is going to be easier, and that is mass stream function.
And then you won't get people like me being like, wait, what?
Yeah. You don't have to tell this is a stream function. Just tell, oh, the tracer just to transport along the side. Yeah. Otherwise, you can say many things about this from this one. Like, we don't know.
That's it. You are right. So
it's not a very good proof or evidence. I think it's good.
Okay.
Yeah.
Thank you.
You're talking good, yeah.
Thank you. I need to practice again. Oh my god.
More practice will always happen.
Thank you.
All right. Any last words, Kobe?
No, but thanks for hearing me.
All right. Bye.
Bye.
I can end the
Yeah, I think like you can put more introductions in this talk.
I sure we do. Yeah, that's the thing. So I'm kind of I'm not familiar with the the knowledge level of people about the atmospheric science.
You just assume they know nothing.
Know nothing.
Yeah. Like imagine that you're talking to a geomorphologist. They don't need to know about the atmosphere.
Okay. Yeah.
Think about people doing plate tectonics, seismology, fossils, isotopes.